whether some special symbol, I don't know, symbol Z, appears in the string. Then it's very easy what you do. You just have two states. Symbolically, you can explain what you are doing by a picture. So, if you see, initially you are here. If you see any symbol except Z, you just ignore the symbol. And if you see a symbol Z, then you switch to another state. And then you can see whatever you see, Z or not Z, you are still in this state. So this is called initial, in this picture, this is called initial state. These arrows are called transition table. Table because you can represent them as a table, which says where you should go if you are here and you see this. And this is called accepting state, which means that if you finish in this state, then you say yes, your string contains Z. And this initial state is not accepting state, because if you finish here, then there is no Z in this string. So I don't give a formal definition, but it's more or less clear that this picture indeed checks whether Z appears. So now imagine we want to check that Z appears immediately after Y. We have two letters, special letters Y and Z, and we want to check that Z appears immediately after Y. Could you draw a picture of an automaton for this task? How it will? What should you do?
Will there be three bubbles?
There will three states, three possible, and so let this, for example, this is initial one, before we see anything. So what do we do?
It circles if it doesn't find Y.
So if it's not Y, then we are in the same state. And if it is Y, we should move to some different state.
There you have one chance to get Z, otherwise you go back to your initial state.
So if then we see Z,
There it is. Well,
we go to the third state. And after that, we always anything.
yeah.
Well, if you've got another Y, then you stay there.
And
Yeah.
so the only thing which is not defined yet, what do? We are here. So if we have another Y, we stay there. Yeah. So if we have Y, we stay there. And if we have not Y,
Go back.
we go back.
That's it.
Yeah. Now we have all the cases for yeah. And for example, if we have just replace this, if Z appears somewhere after Y, how should we change our automaton? If we don't require CP immediately after Y, then we should make some changes. Which one?
We just stay at that second state.
Yeah, now if we are in the second stage, we know that Y already appeared, and we see some letter which is not Y or not Y, we should not go, we should still be in the same state because we are still waiting for Z and know that. Yeah, so this is easy, very simple automata and rather easy tasks, but we can construct much more, actually much more difficult things can be recognized by finite automata in the same way, but by a more complicated automata. And there is a whole theory developed by Klimi, which proves that there are some kind of expressions which are called regular expressions, which involve these stars and repetitions and union and concatenation and so on, and they more or less correspond to finite automata. So there is a Klimi theorem which says that for any finite automata, that set of strings which are accepted by the automata as a regular can be described by a regular expression, and on the other hand, for every regular expression, there is a finite automata which recognize exactly these strings. And if you if you look at many utilities, like in text editor, when we look for something, or in compilers, there is a phase which is called lexical analysis, and so on. All these algorithms are based on this theorem. So it's a very practical theorem. So this, I think, maybe it's rather long theory, so it may require, I don't know, how many?
3 or 4 lectures.
Yeah, so it depends what we want to cover here.
Yeah, you need to start with other examples.
Yeah. So it's very nice elementary theorem, and so it's worth trying. Also, it gives some intuition for more complicated things, which are called pattern matching algorithms. If you, for example, if you perform a search in text editor, what is the fastest way to find the if you have some pattern and you want to find where it appears in the text. So there are fast algorithms for doing this. The first is called Knuth-Morris-Pratt algorithm, and there are some others. So there is some kind of, and they are based on this finite automata theory. So it's also useful. So you see that the whole, it's for biology, it's very important because they have millions of sequences of very, very long sequences of DNA, and they don't know what to do this. So they try all the possible algorithms to find some kind of pattern and what is happening and why it's happening and what are the common elements of two sequences and so on. So since now biology is one of the most fashioned things, this you see this. If not the biology, you never will have such thick books on string algorithms. So we should also cover a bit on them. Yeah. Okay. So we should stop. And next time, I think you will start with this and